Okay, so friction. We've talked about friction being responsible for gripping our shoes with the floor to help us walk, right? Remember day one, we talked about walking. I push back on the ground and the ground pushes me forward. And yes, it's friction. Because if you were to walk on an icy surface, would you be able to do the same stuff? No, you'd have to be more careful. You'd have to, there's less friction with the ice. And that's actually the first big idea. Friction varies based on your surfaces. And so I could wear the same tennis shoes on ice and the same tennis shoes on concrete here. So the shoes are the same, but there's a different surface. And so it's different. Okay. It's a different amount of friction. It's a different motion. And so I could also change my shoes, right? Right now I have rubber grip shoes on with the concrete, but what if I got some slick, maybe, I don't know, sandals or house shoes? They weren't rubber bottom. There's less grip. And so you can change the shoes or change the surface or both. And when I say shoes, I'm just referring to that walking example, but this works with tires on the road. Do we buy forever tires? Do tires last forever? No, you got to replace them. It wears down. There's less grip with the road. Make sense? Okay. And so that gripping and slipping friction that we had talked about originally, and I'm going to slide to the right-hand side to be giving some notes here. And so we have that slipping friction. Now, the nitty-gritty name for that, it's still slipping, but it's when your two objects are sliding past one another. And so we call that officially kinetic friction. Okay, it's parallel to the surface. That's always going to be true. Okay, and kinetic, hopefully you remember from, I don't know what grade, 8th grade science, I'm not really sure, but you've hopefully studied kinetic energy before. Kinetic means the object is moving, okay? So your object is moving. The two surfaces are slipping past one another, yes? Our equation for kinetic friction, and this would be if I slid a box across the surface, okay? It's that where we take our hands and slide them past one another. That's kinetic friction. My object, my hands are moving against each other. And so this is kinetic friction. This can produce heat, just FYI. I rub my hands together, they get warmer, right? Now, we don't study thermodynamics. Later, when we talk about work, we'll talk about the work done by friction. So this is later. I'm just letting you know, long term, kinetic friction is the one that produces heat. We do have an equation for kinetic friction, and it's kind of on the formula chart. The force of friction is equal to this Greek symbol mu k times Fn. What is Fn? Normal force. What is FF? Frictional force. But what's this mu? And with a subscript k, it's called the coefficient of kinetic friction. Okay, coefficient. What is this coefficient? Okay, this is what's surface, or I'm going to say material dependent. So earlier I was talking about my rubber shoes versus, bless you, versus maybe some house shoes that were real slick. They didn't have a rubber bottom, okay? Or sandals that don't have a rubber bottom, right? And so the different material gives you different coefficients of friction. Now this is a really long list. If you Google coefficient of friction, whether you say kinetic or static or what, Wikipedia has a really big table. okay? You do not have to memorize the coefficients of friction, okay? And so don't try to memorize, but low, mu close to 0 means very little friction. What type of material has very little friction? You know this. Very little friction, so little that we typically say frictionless. But there is a little bit, I heard it. Ice. And so this is like your ice. So with a coefficient close to 0, it means very little friction. What about a coefficient? And I'll explain why we kind of maximize at 1. Most of your coefficients, 99.9% that we'll deal with, are less than 1, okay? Now in real life, there can be cases above, but in AP, I don't think I've ever seen they give you a case where it's greater than 1. So if it's close to 1, meaning like 0.99, what does this mean? Well, it means a lot of friction. And so these coefficients, how do we get these numbers? Experimentally, of course. We have 2 controlled surfaces. We have a controlled procedure, and I'm going to show you a video clip here in a second of the, oh, it works, okay. A video clip of how you can collect experimental data to calculate mu, okay? Mu, coefficient of friction, is not written on the bottom of your shoe, okay? It's not a known value, it's dependent on your surfaces. And so if I use that equation to solve for mu, I would need to divide friction by normal force. So to get a number less than 1, typically, 99.9% of the time, your frictional force is less than the normal. Previously, I had said that frictional force is smaller because it's a fraction of. Well, these coefficients are typically in decimal form, so 0.2, 0.3. That's like saying a percentage of, right? 20% of, 30% of. Everybody good? Let's talk units. What's the unit for this coefficient of friction? Well, you take a force divided by a force, a Newton divided by a Newton, which is what? What's a Newton divided by a Newton? 1. It's nothing. And so is no unit. They say it's dimensionless. Dimensionless. And so it's not a variable with a unit. We don't have that very often. Most of our physics variables have a unit. This is our first one that doesn't have a unit. It's not the only time in physics this happens, but for this unit, I believe coefficient is the only one without a unit. Everybody feel okay? Another piece to this equation, so frictional force, it is what it is. Oh, another note, back up here with the motion, okay? I want to add in, we said it's moving, okay? I'm going to add on here at any speed. It doesn't mean that, oh, a higher speed has more friction. A lower speed has less friction. That's not how friction works. You're either slipping past each other or you're not. And so it doesn't matter what the velocity, or if you have a constant velocity or a constant acceleration. If those 2 objects, your tire in the road or your shoe in the floor, whatever it is, if it's moving, one kind of kinetic friction, one value. Good deal? And so to change the amount of friction, we can change the coefficient, change the surface. Or look at the Fn. Fn, we've already learned with elevators or whatever, shopping carts, lawnmowers, we've learned that normal force is not always constant, right? And so if normal force changes, well, so does your frictional force. And let's look at that shopping cart example. So I've got my cart here, my podium, whatever you want to call it. What if I push down on it? What did we say previously about the normal force here? Equal to the weight, less than the weight, or greater than the weight? If I'm pushing down and forward. If I'm pushing down, same direction as gravity, then the one up is going to be greater than gravity, right? And so, wait, what did I just say? Did I say it right? If I push down, same direction as gravity, I've got two downs, right? A vertical component of my applied force and gravity down, normal force is going to be greater, right? And you can think about it at the molecular level. If I'm pushing down on an object, those molecules at the contact are grinding into each other more, right? There's more pressure, and so there's going to be more resistance. There's going to be more friction. Yes? What if I lift up right here? I pull my shopping cart back. If I am lifting up, then the pressure at the floor with the surface is going to be less, right? And so the floor pushes back up how much? Less. I'd have two ups for the one down gravity, okay? And so normal force is not always a constant. Mu is not always a constant. So frictional force may not always be a constant. And so just be careful there. You want to read very closely. Everybody good? That's kinetic friction, AKA slipping or sliding friction. So what about gripping? And so now, gripping friction, we're going to give it a more official, more what you'll see on the AP exam, okay? It's called static friction. Static means stationary. Stationary, static, gripping. And so now hold on. Actually, stationary, I'm going to put in quotes. Previously, we had said that walking depended on grip. Tires on the road depended on grip, right? You can have a moving car that has grip with the road, right? That's how the tires turn. For me to walk and put my upper body in motion, I have grip with the surface, yes? But the stationary part that I'm talking about is if you look at my foot with the surface. So I can demonstrate this. It's just walking, so not very, thrilling. But when I walk, my body moves. But when I walk, am I slipping with the surface? My foot remains in grip with the floor. My foot is not moving at that moment relative to the floor. Does this make sense? And so when we say static, we say stationary, but really it's the gripping. If there's grip involved, tire on the road, foot on the floor, you can have a moving object, but I'm going to add here stationary at the point of contact. Okay. Now I feel better for walking and tires on the road. It's stationary at the point of contact. Everybody good? Okay. is going to look very, very, very similar, but a little different. And so we've got the force of friction. This is, you can put an S on this one now. I can go back and put a K on the kinetic, but the static frictional force is equal to or less than, the coefficient of static friction, mu S, times the normal force. Okay. So what's up with that less than or equal to? Okay. I'm going to pause here. I'm going to show you a YouTube video and hopefully showing it through Zoom. Doesn't glitch too much. Give me 1 second. So where I'm going to actually flipping physics. Some of you may have watched his videos. Actually, I have his website bookmarked. I'll do that. Okay. And so we're in dynamics, AKA forces, how objects move. And I'm going to look, you can see all the videos he has. I'm going to look for the experimental friction. I think it's this one. So it's just 3 minutes. Oh no. Okay. And so this video, and by the way, this is probably my favorite AP Physics resource for video learning. He has a lot, and so don't ever try to watch them all in one night. That's pointless. But if you want to, if we talk about friction, he has others. And so if you want to kind of get a second viewing, but you don't want to watch Ms. Earhart, this is my #1 that I would recommend. Plus, on his website, you can actually download the lecture notes. And so he has video notes for every single video on his website. If you go to YouTube, the video notes aren't there. And so you don't actually have to write down everything you see in the video. This is not required. It's just, I'm telling you, he's my favorite. He's a little quirky, tie-dye guy. He's a little quirky, but he has a lot of good, in-depth, nicely edited, updated videos, okay? Okay. So you know a little bit about the 2 kinds of friction. We're going to take a look at an experiment, okay? And what I like about this, you're going to see the experiment, and then he overlays what you see on the computer, okay? If we were to do this in real life, you'd have to watch the experiment, and I can't slow motion real life, and then you'd have to look at the data collecting program. So here we go. Good morning. Hold on 1 sec. I want to make sure the sound is going through Zoom.
As I pull on this wooden block using this force sensor and this string, Billy, could you please give me the free body diagram of all the forces and their directions that are acting on the wooden block?
Sure. Flippin' physics. The force of gravity is down, the force normal is up, the force of tension is to the left, and the force of static friction is to the right. Static and not kinetic friction because the block is not sliding relative to the table.
Can y'all hear that in the back?
Thank you. Now, in a moment, we are going to draw a graph of the force of tension, and it will include the force of friction. In order to understand that graph, we need to first sum the forces in the x direction. Bobby, could you please do that?
The net force in the x direction equals the force of static friction, which is positive because it's to the right, minus the force of tension, minus because it's to the left. All that equals the mass of the block times the acceleration of the block in the x direction. However, the block isn't moving, so the acceleration in the x direction equals 0. Therefore, the force of static friction equals the force of tension.
Which means, as long as the block is not moving, the force of static friction and the force of tension have the same magnitude. Now, as I pull on the force sensor, we get a graph of the force of tension as a function of time. And because the block isn't moving, this is also a graph of the force of static friction as a function of time. And you can see that force of static friction increases and decreases to prevent the block from moving. Let's start over with a new graph, only this time I'm going to steadily increase the force of tension until the block starts to move. Okay, I am slowly increasing the force of tension and therefore the force of static friction until the block starts to move and it switches from static to kinetic friction. Let's watch that one more time and carefully note when the block starts to move. It starts to move right now. All right, let's take a closer look at that graph. You can see the first part is all static friction when the block is stationary and the force of tension equals the force of static friction. This means the maximum force of static friction is also the maximum force of tension. Then the block starts to move and the friction switches to kinetic. After the block starts to move, the force of tension decreases because, well, actually, Bo, why do you think the force of tension decreases when the block starts to move?
Because the coefficient of static friction is greater than the coefficient of kinetic friction.
We are looking at a graph that shows that it is harder to put something in motion than it is to keep something moving. Very nice, Mr. P.
Thank you, Bo, and thank you for learning with me today. I enjoyed learning with you.
Okay.
Good morning.
Okay. So hopefully we learned a little something from that. I'm going to add some more things to our notes. Oh, I'm sorry. Yes, I see now. New share. All this wonderful technology, but you forget one button. Okay, thank you. And so we learned a couple things in there, hopefully. And so first thing I'm going to put down is what he said there at the end, that the static coefficient is greater than the kinetic coefficient. And so mu s is greater than mu k. And you're like, well, why is that? Well, again, experimentally collecting data among a lot of different surfaces and objects, this is what it is. And he said it's harder to put something in motion than it is to keep something in motion, okay? Have you ever tried to push something really, really heavy? It might take two people to get it moving, a lot of applied force, but maybe once it's moving, one person quits and it's just one person pushing, okay? And I'm gonna keep with the shopping cart example. So here's my shopping cart, right? We already said that when I push at an angle downward, the normal force is bigger, right? But wait a second, normal force, gravity, the weight also comes into play, right? Because it's another vertical force. What if I fill my shopping cart full of gold bricks? Just work with me, okay? Wishful thinking on my part, maybe. What if I fill the shopping cart with gold bricks? Why gold? Why bricks? What am I doing here? Making it more heavy, right? So imagine my shopping cart in front of me, full of gold bricks, not just a bunch of cereal, Lucky Charms that's really, really light, okay? When I go to push it, like I would with Lucky Charms in the cart, I go, oh. But I go to push it the same la-di-da applied force. Does it go anywhere? No. I can't push those gold bricks the same way I push my Lucky Charms. And so have you ever tried to push something heavy and maybe somebody says, you gotta put your back into it, right? And I don't know where that phrase came from, but if I really had a heavy shopping cart full of gold bricks, I'm gonna not only increase my applied force, but remember with friction, a lower frictional force, I may not be able to change the surface, but I can change my normal. How do I decrease my normal force when I'm pushing a shopping cart? What if I get at a smaller angle, right? So I'm actually lowering down so that I push it horizontally. Now the normal force is not as big as when I was pushing down on the object, right? But if I get level with it to push in this stance, if you can see, right? When you go straight push, then I'm more likely to be able to push those heavy gold bricks. And then notice once it's in motion, I stand straight up, right? And so it's harder to put something in motion than it is to push a moving object. Has anyone's car ever broke down and you got to push it off the road? No, just me? Okay, so, today, if there's an empty parking lot, safety first. Now you probably want to put your car in neutral. Don't actually like disable and tear your car up. Just put it in neutral. Get out, empty parking lot. Okay, make sure you're not aiming for a tree. Maybe one of your friends is in the driver's seat and all they're going to do is steer. Okay, put it in neutral. Try to push your car. It's hard to get it moving, so maybe your friend has to help you get it moving, but then once it is moving, you can push it a lot easier, okay? I have a YouTube video somewhere. It would take too long to find it right now. I'll look for it and maybe send it out. There's a 4-year-old pushing a car. And you're like, what? Dad helped get it started, but after it was moving, 4-year-old could push the car. Because kinetic friction is less than static friction, okay? And if you were to use your hands, slipping, no effort really, but gripping, kind of put your fingers interlaced. If I'm trying to grip, then it's gonna take a lot more to make those particles slip. Question? Kinda, probably, yeah. But here we're talking about like at the surface level and how you can vary the normal force. And so I'm just talking about how you change the frictional force. That's all I was really going at here. Okay, now one thing I haven't, so that's static is greater than kinetic, okay? One thing I haven't addressed yet, he kind of did in the video, is that less than equal to. And that's actually what's on the formula chart. There's no K's and S's. What they have on the formula chart is, it looks like one equation, but it's really 3 equations in one. Now kinetic is just kinetic. I didn't give any alternate. What if I give you 2 variations of static friction, okay? Do you remember how that graph reached a peak? Now I'm doing a simplified graph. Real life is more ziggity zaggity. I'm looking at maybe just overall trends, okay? Average trend. And so this applied force or tension force, and then on the bottom, I don't remember what he plotted on the axis, but I'll get that here in just a second. But this initial part before the peak is your static portion. You can push a little and have a little grip, a little static friction, right? So maybe this is, 10. I can push a little more and it's still not move. There's still grip. But if I increase my applied force, well, if it's not moving, it still has to balance with friction, right? And so this is your FA is balancing the static frictional force, as long as you're not moving. So this is at rest. What if I push a little more and it's still not moving? So if I increase my applied force, friction, static is still increasing. I'm not changing the surface. All I'm changing is my applied force. And then what if I reach that point at which grip no longer happens? It immediately changes into slipping or kinetic. And so that's the transition point. And so this is a maximum location. This is maximum frictional force for static. So static friction, here's our alternate type of equations. It can equal your applied force for balancing forces for an object at rest. Or we can say that your static maximum is equal to that mu s, that's the coefficient of static friction, times the normal force. So this is that maximum tipping point, if you will, okay? It's not going to move unless you overcome and reach that maximum. This graph that you see here, I'll be drawing all year, okay? Because even when we get to work and energy, I've already kind of showed you, work relates back to forces, it relates back to friction, okay? And so one equation on the formula chart is really three big ideas in one. And then if we kept that, graph going, as soon as grip is no more, then the object slips. Now notice there's only one value, okay? Again, real life is a little ziggy-zaggy. He was pulling on it. He was not a robot, okay? But you just have one value for that kinetic frictional force. Everybody good there? Still, coefficient has no units, frictional force newtons, normal force newtons. Can you have static and kinetic at the same time? Not at the same point of contact, okay? Because at the point of contact, if you focus on that, you're either gripping or you're slipping, okay? Okay. Let's try some examples. That graph, you'll see me do it over and over and over, okay? I may not take the time to label every axis, but that up to a max, and then immediate drop to a horizontal line. That's demonstrating the static can grow to a max, and then kinetic is one constant force. Okay, let's do some rankings here. And so we've got a box, it's got a mass M, and we're going to do 5 different things with it. We're going to pull on it, so there's a force, there's an applied force, and notice the difference is A, you pull at 0 degrees. B and C, you're going to pull up at 30 and 50 degrees. And then D and E, you're pushing down, so this is like your shopping cart, at 30 and 50 degrees. Rank from highest to lowest the coefficient of kinetic friction. And so they don't really tell us up above if it's moving or not, but if they're talking about kinetic, you have to assume they're all in motion, okay? And so coefficient, does the coefficient care how you push? The coefficient is surface and object dependent. And so assuming that all of these are the same object, and there's no indication that one example is ice and one is concrete, we'll assume they're all the same surface. And so these are all going to be the same. Okay. Normal force. This is old stuff now, right? Who's going to have the greater normal force, the greatest normal force? When you push or pull horizontally, when you pull upwards, or when you pull down, push downwards? When do you have the greater normal force? When you're pushing down. And so that's D and E. So which one would have a greater normal force? And we could draw a full diagram for D just to, kind of refresh our memory to see it again. We've got a gravitational force down, and then we've got an applied force down and right. And then friction is going to be parallel to the surface. Normal force, you would really want to draw in those components for FA. And so normal force is bigger than the weight, and it's going to equal the weight plus your applied y component. So who has a greater y component, 30 degrees or 50 degrees? 50. And so 50 would have a greater y component, therefore you're adding to the same gravitational force more Fay. And so normal force would be greatest for E, and then D, and then who? Who would be next greatest? A comes next. A would have Fn equal to Fg. And then B and C, what would they look like? Well, we got the same gravity, but now I'm pulling up. And so normal force doesn't have to be as big, right? Who's going to be greater? Normal force at 30 degrees pulling up or 50 degrees pulling up? At which angle? I just didn't hear. 30, yes. And so B would be next, and C would be the least. C, you're kind of pulling off the ground the most because that Fay would be bigger with a 50 degree. Everybody good there? Okay. Then 3 and 4 rank static frictional force, assume they don't move. And so that static frictional force is going to be dependent. Earlier, I said it was equal to Fa, but I guess I should be more clear now. Can my frictional force that's parallel to the surface, can it equal a diagonal applied force? Can any horizontal force balance a diagonal force? No, you got to do X with X. And so now kind of visualize that X component. If they don't move, then F static friction, the force of static friction, is balancing FAX. So who's going to have the greatest FAX? A. If you pull at 0 degrees and check it, what's cosine 0? It's 1. And so that means I would be multiplying my full applied force. So assume all the F's are, 20 newtons or whatever. If you don't have to break it up into components, then it is your FAX. And so A is the greatest. Then who? Who has the next greatest FAX? B and D. Does your horizontal differ when I pull up and right compared to down and right? It's still right. And so then it's greater than B equal to D, greater than C, which is equal to E. So whether you pull up or push down, at least in this picture, is not changing your X component. All right. And then we get to frictional kinetic force, right? Kinetic friction force. Assume that they do move. And we already said previously, it doesn't matter if they're moving at 2 meters per second or 20 meters per second, or if they're accelerating 2 meters per second squared. If you move, you're slipping, okay? And so it doesn't matter the speeds. Who's going to have the greatest kinetic frictional force? If they all have the same coefficient, it really just depends on the normal. Say again. Yeah, it's really, so force of kinetic friction, remember I only gave you one equation for that one. It's equal to mu K times Fn. And so mu K is all the same. So it's whatever's true about Fn. So it's the same ranking, same rank as Fn. So E is greater than D, greater than A, then B, then C. Good deal? Okay, so static friction is gripping friction. It takes a lot to put an object in motion. But once it is in motion, it's easier to push because there's less kinetic friction. So now we're gonna have to skip around because some of these have ramps and some of these have pulleys. And so I believe the problem that we're gonna do next is on page, no, let's do page 16. I think the top we can do. Page 16 at the top. You give a box a quick push. Why would they say that? We're not giving it a constant push. So I'm not gonna sit there, if you're watching my podium, I'm not gonna sit there like I was before and constantly touch it and constantly push it, right? A quick push just looks like this. I stay in place, but I push it away from you, right? It's not a constant push. So you give a box a quick push and it begins to move to the right at 10 meters per second. It then slows to a stop over a distance of 20 meters due to friction. What is the coefficient of friction? And so here we're solving for mu. Now, honestly, it doesn't matter if you're doing mu K or mu S. Overall, the equation's the same. The spirit of coefficient is the same. It's just a clarifier, okay? It indicates, hey, you're moving. And so to find this, we know we have to use our new equation. We need to know the normal force and the frictional force. And so how are we going to find those two? Not with an equation on the formula chart. We need to write our equations. It all starts with what? Any force problem, your go-to step one is diagram. So what forces are acting on this box? We got Fg. And we got a normal force going what direction? Straight up. How big do I draw it? It is equal to the gravitational force here. Why is it going to be equal? Well, did they mention any angles? Are we pushing up, pushing down? And at that, it's not a constant push even. So I'm not even going to put FA. No FA. We're looking at the snapshot in time when it's slowing to a stop, okay? Because that's when they're asking about the kinetic coefficient. In the beginning, when it's at rest, it's not kinetic. And so if it moves to the right, what direction will the friction act on it in order to bring it to a stop? Friction will be drawn to the left. And so this is a kinetic friction. So notice I'm going to add in my coefficient. And so that's where I got to solve for in order to get the coefficient. And so step two, F net X equals that frictional kinetic. And I want the force. Don't plug anything in for the force right now. I want that frictional force. So Newton's second law, F net equals what? Ma, and it's a horizontal acceleration. Ooh, did they give me horizontal acceleration? Did they give me mass even? They did not, but hold on. So hopefully you've discovered if they don't give you something, it's okay. Just keep it as M. But acceleration, I can't have everything as a letter. They did give me, it slows to a stop. I know it starts at 10 meters per second, and I know the distance. Can we solve with kinematics for the acceleration? Let's do this, and then we'll call it for today. And so initial is 10. The distance is 20. Final velocity is 0, and we're trying to solve for acceleration. Which kinematic equation will we be using? Third. And so the one VF squared equals VI squared. And so we come to a stop. And so 10 squared is 100. And then I got to subtract it to the other side. Divided by 2 times 20, which is 40. Negative 10 over 4 is negative 2.5 meters per second squared. Okay. And we'll pick up here next class. We'll now use that acceleration, go back to our FNet statement. All right. I'll see you next on Thursday. All right.